All right, so the first part of this unit is going to be the kinetics, which is chapter 17, and on the board back there is I have what pages you should read. So we're just going to go through the very first part of kinetics, and then we'll finish up some of it tomorrow. We do have a lab on Thursday. It's a 2-day lab, okay? So the reaction process is what we're going to talk about first. Of course, you know from just seeing things around you that reactions sometimes take very long time to happen, or sometimes they happen very quickly. And what kinetics is the study of those rates, so how quickly a reaction occurs. Iron obviously rusts very slowly, and fire burns very quickly, and it's because of different things in their reaction mechanisms.
Is it fire on the ocean?
It is fire on the ocean.
Might I ask why?
Probably like an oil spill. Like if you have an oil spill, that's one way to get rid of it, is light it on fire.
That's like a clump of stuff.
It's because it sticks together.
That looks like a glacier.
Yeah. Okay, so reaction rates take into consideration the rate of reaction. That is going to be the study of kinetics. When we are talking about the rate of reaction, we can either be observing how long it takes for the reactants to disappear or how long it takes for the products to appear. It honestly depends on what's just easier to observe, okay? And the units for that is molarity per second. Molarity per second. That is the unit for rate. And we will be calculating those. So, in the video we talked about some of the causes, and we had to talk about the collision theory. The first one is, first and foremost, you have to have collisions, so number of collisions. The more collisions you have, the better. So number of collisions. Those collisions have to have proper orientation, so the orientation of the collisions matter. And then lastly, you have to have sufficient energy of the collisions. If you do not have enough energy, the reaction won't happen. Together, this is all part of the collision theory. So you might want to draw yourself a little line like that next to it and write the collision theory. Okay? Collision theory states that you've got to have collisions, they have to be properly oriented, and they have to have enough energy to be effective. When all of these conditions are met, we call them effective collisions. There's a large portion of collisions that are often ineffective, and so you don't get a reaction. But when you have all those three things in place, or you have collisions with those two things, sometimes it's worded that way, then you have effective collisions, and then you have a reaction that takes place. Some things that help speed up a reaction are, we're going to talk about in a second. This is just a visual for you to see some of these collisions don't happen because they're ineffective. Same thing with proper orientation. If they're not oriented correctly, they won't react. Okay, so energy diagram. We saw this energy diagram when we were doing the thermochem unit, but we're going to talk about another concept of it. The energy diagram is going to represent the energy pathway of the reaction. Okay, at the top, right up here, so draw a little arrow because you're going to fill this in. This is called the activated complex. And when you have that activated complex, you got a couple of things going on. You can have bonds breaking and bonds forming. So at that time, bonds are breaking and they're forming. This is different than the products and the reactants. It's like kind of an in-between state.
They break and form, or
they break. Well, first of all, they break and then they form the new ones.
Then form.
That's why I said breaking and forming.
Yeah.
Got to break them before you can form new ones, right? Okay. The energy required to reach that activated complex is called the activation energy. And if you look at that graph very closely, I'm going to pull it up on the next screen because it's bigger. But if you look at that graph very closely, the activation energy is between the reactants and the top of that activation complex or activated complex. Okay, For an endothermic process, it is a larger activation energy because it's from here to here. And then if you recall from thermochem, the difference between the products and the reactants is delta H. So this would be delta H over here.
Sorry, I forgot about
Okay? So if you recall, if you have an exothermic reaction, what is the sign of delta H? Because remember, delta H is the sum of the products minus reactants. If it's exothermic, what was delta H? Negative or positive? It was negative.
Negative.
Okay?
Wait, I thought you said products minus react. Oh, yeah, negative.
Okay? And in an endothermic reaction, delta H is positive. Okay?
I probably don't believe out.
Okay? So that is what the energy diagram looks like for a exothermic and endothermic reaction. Remember, this up here was that activated complex. And what's going on there? Breaking and forming bonds. Okay.
It's at the top of the curve.
It's at the top of the curve. If a reaction does not have enough energy to make it to the top of that curve or the top of that hill, it will not happen. Okay, but once it gets that enough energy, it reaches there, then it starts falling back down. Okay, so that's the highest amount of energy there. Okay, these are the 5 things that can affect the rate. We have the nature of the reactants, temperature, surface area, stirring, and the catalyst and concentration. Yes?
Next year you should make them all on one page.
I thought it was. It was when it was on my paper. When I printed it out and took it, and I got them back, and I was like, it was whenever I had it on my computer.
It's all right.
Okay, thank you. I appreciate that. All right, so when we are talking about these 4 things, let's talk about a little bit each one, and that's all we're going to do for today. For nature of reactants, first and foremost, it depends on the reactivity. Okay? Obviously, if we have something that's super reactive, like a group 1 metal, it's going to have a very fast reaction. Okay? Because it's already very reactive. But if I'm dealing with something, say, like palladium or silver or gold that's not quite as reactive, then that rate would be a lot slower. So the reactivity makes a difference. Ionic reactants, things that will transfer electrons, they will occur almost instantaneous. And that's because the electrons have already been transferred. And so if you're dealing with an ionic reactant or an ionic compound, it's going to be very quick. And of course, if you're dealing with molecular, it's going to be a little bit slower because then you have to rearrange all those electrons. And molecular means what kind of bond? Molecular is covalent. So if I'm dealing with something that's covalently bonded, it takes a little bit longer to react. So the nature of reactants is the first one. The next one is going to be, I believe, temperature.
Yes.
Okay. So for a temperature, if I increase my temperature, I increase the energy of my collision. Okay. Remember way back we said heat them up, speed them up. And so if I heat up my particles, I speed them up, and if I speed them up, what does that do to my kinetic energy? That's it. Thank you. Okay? And that's because now when my particles are moving faster, they have more energy, so now more collisions will have enough energy to overcome that activation energy. So that's why heating up the reaction increases the rate. Remember when we're talking about in terms of breaking and forming bonds, it takes energy to break bonds, so that's endothermic, and energy is released when new bonds are formed, so that's exothermic. So breaking is endo, forming is exo. So here's just a visual for temperature. When you have a lower temperature, this little point right here is the amount of particles that actually had enough energy to form. And when the heat is, or the temperature is very low, you don't have that many particles that had enough energy to overcome the activation energy. But if you heat it up, now your particles are moving faster. Now you have quite a bit more particles that are able to overcome that activation energy because they're moving with more speed, more kinetic energy, so they have a better chance at becoming an effective collision. Surface area and stirring, remember the solution unit, we said heat it, crush it, stir it. Kind of all the same thing here for increasing a reaction rate. That's the same things that increased how quickly something would dissolve is some of the same things that will increase a reaction rate. And for crushing it, of course, you want small pieces, which gives you a large surface area. Stirring has that same effect. Because remember, when I'm stirring or agitating it, I'm constantly introducing fresh solvent particles. So in this case, if I'm stirring it or shaking it up, I'm constantly introducing their fresh reactants to each other to have that reaction. So one thing that kind of gets backwards in some kids' heads, and I think it might have caught a couple of you on the test when we did heat it, crush it, stir it, large surface area means small pieces. And so somehow some people got that backwards in their head. Large surface area means tiny pieces because it's more surface for it to react. Okay? So in the case of, say, a sugar cube versus, say this was my sugar cube versus smaller pieces, the only thing interacting are these outer particles. Whereas I break it up, I got all the outer particles of these interacting. Yes?
On that last slide, what was that? Remember, more fresh solute to solvent interactions in solution unit? Question mark?
Yeah, I just talked about that. I
Why
literally.
is there a question mark next to that slide?
I'm saying, I'm asking if you remember.
Oh, okay. I was like, I don't know what's happening there.
Yeah, I'm just asking. Remember, like as a question. Okay. Presence of a catalyst. By this point in your life, you usually know what a catalyst is, but a catalyst is a substance that increases the rate of a chemical reaction, and here's the key, without being changed or used up in a reaction. Okay? What the way a catalyst works is it provides an alternate pathway that has a lower activation energy. So it provides a way for it to get there quicker. Okay? And in your body, catalysts are called what? Enzymes. And you have them all over the place in your body. Otherwise, most of your processes that work in your body wouldn't work, or they would take too long. Okay? The opposite of a catalyst is something that would slow down a reaction, and it's called an inhibitor. And it works exactly the opposite. Instead of providing a new pathway with the lower activation energy, that pathway has a higher activation energy. And preservatives work like that. We don't want food to spoil as quickly, so we put preservatives in them so it slows down that process. Okay, a lot of medications for illnesses sometimes are inhibitors to keep that process from happening as quickly in your body. Okay, so you have this graph, and we're going to add in the inhibitor as well. Okay, so we have our reactants and our products. Notice when I have a catalyst, that is not changing. Okay, my reactants and products are starting and ending at the same place, regardless if there's a catalyst present or not. So it will not change. Remember, this is delta H. It does not change delta H. Okay, what it does change is the activation energy. We show activation energy by EA, and I forgot to show you that in the last slide. So activation energy is EA. Okay, so notice that EA goes from being from here to here, and it lowers it. If there is an inhibitor present, you would draw it like that. So add that line in. And now you would have a much larger EA, and so there would be less collisions that would be effective, so it would slow down that process, whichever process this happened to be. But the main thing to know on that is it does not change the overall energy or the delta H of the enthalpy, but it does lower your activation energy in the case of catalyst, or raises it in case of a inhibitor. Okay. And then last part for today is increased concentration of reactants will cause more collisions. And when we have more collisions, we have a better chance at having effective collisions. Okay? And then for gases, we would want to look at increasing the pressure. Because if I increase the pressure, what would I be doing to volume? Making my volume smaller, so now my particles would be closer together. And so then that means I would have more collisions in a smaller amount of volume. So that would also increase it.
Adding more gas to the same size container, volume increase?
Yes, but I'm saying when you're talking about gases, you have to remember that I can theoretically increase the concentration without adding more gas to it by increasing the pressure. Yeah.